Very good. All right. So welcome everyone to the February Self-Driving Cars 101 event. I'm very pleased to see you all here. My name is Brent Shedd and I will be your host today. I'm also the CEO of Zeeco Robotics, which is providing our Zoom connection this morning. So I want to give a quick shout out to the fabulous team at that. Zeeco, for those of you who do not know, we develop autonomous vehicles for airlines and cargo operators. So think like baggage and cargo tractors. And so I'm really interested in the presentations today because safety is super important for us, as you would imagine, in the aviation space. If you'd like more information on Zeeco, just reach out and I'll be happy to fill you in. But I also want to acknowledge Grant, who is producing these events for us this year and has done a great job of putting this together. So I want to give him a shout out. Our format for today is a company showcase, which means that each of our speakers will have 10 minutes to share what their company is doing to make autonomy safe. We have a great lineup of speakers. As you can see, we have Sharad Agarwal from EasyMile, and I just want to apologize ahead of time if I mispronounce anybody's name. That's right. My fault. But super pleased to have everybody here. We have Bastien Beauchamp from Important. We have Mario Enrique Cruz Torres from IVEX, who is with us now. We have Matthew Worm from Siemens, and we have Zib Benyamini from Fortelix. And we're going to go in that order. If you have questions for any of the speakers, please put them in the Q&A. And we will do our best to address those at the end of the event. If we're not able to get to all the questions, we will do our best to source the answers for you and post them on the meetup page. So feel free to put those in there. This is being recorded, and we'll make the recording available as soon as possible after the event, and I will send a note out to everyone as soon as that has been posted. So with that, it is 10:04 in the morning in Silicon Valley, and I want to welcome all of our speakers and all of our attendees. And let's go ahead and get started with Sharad from EasyMile.
Okay, I will set up the screen. Please confirm, Brent, that we see.
We can see it.
Okay. Well, thank you. Thanks for the introduction. I appreciate the opportunity to talk to everybody about safety and how EasyMile is approaching it. It's clearly the #1 focus for anybody in the AV space. So this is an ideal topic for us to start with. Just a little bit of background on myself to say maybe why I'm relevant to this topic and where we can add some value. I've been in the transportation industry, primarily the passenger space, for the last 15 years. I am based in Denver. Most of my career has been in public transit in the areas around that, but also not just being in public transit, but trying to find ways to disrupt it and change it and move it towards the future. That's really been my mission and my goal, and thankfully part of my career, to be able to actually put that emphasis on changing public transit, and autonomous vehicles clearly being one of those areas that will be quite disruptive. About EasyMile, take a few minutes just talk about the company itself. So we are a now 7-year-old startup. So I'm not sure the designations anymore, but I think 7 years is still considered a startup in our perspective. We do have a very nice global presence. Primarily, most of our focus has been on Europe and in the US. A very large amount of highly intelligent people building our software. Almost now 250 people in the company with all kinds of different nationalities. So we have a very diverse company, really focused on autonomous technology. We've been very fortunate to be funded by some of the top companies in the world, with Continental AG, Alstom, and then the French government is one of our investors. So giving us some validation on where we think we're headed with our technology. We have some of the top players, especially when it comes to automotive safety, Continental being one of the leaders, and knowing that they're one of our key partners, investor, partner, customer, has been really good for us. So maybe to summarize what the company does, we have 2 really key products in the US market that are probably of interest. The EZ10, so anybody that knows EasyMile, you're most familiar with the EZ10. We have over 150 of these vehicles running worldwide and 30 of them in the US. So we have quite a bit of a presence with the vehicle. It is a 6-passenger with seatbelts and up to 12 without them. The vehicle runs up to 16 hours on one charge, only about 8 though with any kind of HVAC, depending on where you are. I think for us, in a very quick separation in the AV space, we are really focused on a commercial speed application. So right now we're running at 12 miles an hour with our target range to be within that 15 to 20. We're really focused on pre-mapped routes. So things like public transit, shuttles, amusement parks, things that you would see on a lot of repeated routes in high density areas. That's really where our technology is focused in the passenger space. And so we aren't looking to be a door to door anywhere, anytime. We're really focused on being in this niche market, which is public transit, shuttle engagements and things like that. So that's really where our focus has been. And right now the product we have on the market is the Easy 10. But in the next really about a year, we're planning on launching in Q1 of 2022 is a US custom product. So this might be the most common bus you see anywhere. I guess my European colleagues probably are not so familiar with this vehicle, but definitely those in the US have seen these vehicles pretty much everywhere you go, every airport, every campus, just running on the public roads. This is the most common vehicle in this passenger size. And so we are looking at building, we've already started the production of this vehicle, and the first prototype will be on the road in Q1 of next year, in Houston Metro is our first launch site. And this vehicle initially will have a top speed roughly what we're doing now, which is in the 12 to 15 range, but we're looking to get the speed up to 25 maximum speed by the time the product is in full engagement. So that's kind of a little bit of a background on EasyMile. And so I want to dive into now where our commitment to safety comes in. So just as a starting point, when you think about AVs, there's always a question mark is how are we going to really make AVs safer? So I look at the four major areas of where the traffic accidents and fatalities have been, and where AVs can really bring an immediate impact once they're commercially available on the road. So clearly, drinking and driving, that's one that we don't have to worry about too much because AVs aren't going to be sitting at the bar and then driving home later. So we know that's one area that we'll be able to address. Speeding, you can't really get an AV to break the law. So it's really more or less, this is the speeding. You're not going to have a lot of concerns from that. The speed limits that are posted are going to be the speeds that we travel at. Clearly, just driving distractions are not going to be a problem because they don't text, they don't make phone calls, they don't look at other people. So AVs will be really focusing on the road at all times. And finally, the bad weather, I would say this is a most likely scenario where the AVs will be much better. I mean, if you think about it, we don't even put windshield wipers on or fog lights or any of that stuff on AVs. So there's a lot more confidence that during bad weather, AVs will be much safer in that driving space. From the EasyMile perspective and how we're going to address these different areas, we break down our safety concept into three areas. The first one being on the localization. So simply define what localization is how does the vehicle know where it is? It needs to have a starting point to know where it's at. And it's important because AVs do operate on maps. So they do require this location to really ensure that they're in that mapped area. So if you deviate from the mapped area, then the vehicle should not operate. And so that really adds to the safety is that the vehicle will always know that it's only going to it's staying within the map that it knows where it's headed. So there's no unknowns for AVs, at least at this level. I mean, level 4 is really what we're talking about, which is pre-mapped areas. So the vehicle knows where it's going to be, and that helps increase the safety of it. From our perspective, we're using a number of different areas for localization and to a fusion to know where the exact accuracy of the vehicle is. And one thing for us is that if the vehicle even deviates slightly, the vehicle will slow down or stop, depending on the action that we've pre-programmed. What we also use, and I think a lot of the companies do, is we incorporate NRTK GPS correction. So not only do we have a general GPS signal, but we're actually correcting it to be even more accurate down to 5 millimeters. And so if you imagine your normal cell phone, your GPS, you might, if you're getting picked up by a ride sharing company, it might show that you're on the other side of the building. That's not an option for an AV. If you're that far off when you're talking about GPS, you could be completely in the middle of other oncoming traffic. So we have to be very, very precise in what we're telling the vehicle and where it needs to be. And so that's where our localization is our first standard when it comes to safety. On the second hand, the second piece of it is the navigation. So when we simply put, that's how does the vehicle know where to go? What's the trajectory that we've programmed it for it to go? And it needs to know that it stays along that route. And since they operate on maps, they need to always know where that information is for them to continue to travel along that. So anytime they remove their function from that map, there should be some corrective action that's required immediately to get back into their map. oftentimes to simply stop, reevaluate where you are, and make a decision on what to do next. And so I think that's an important piece about vehicles, that if you're deviating off of route, going to new areas, that's going to be a real challenge. So for us at EasyMile, we really looked at saying, okay, here's the site map. We pre-program it. We pre-program the trajectories. We pre-program all the specific behaviors. So if there's the speed is always preset, pedestrian crossings are identified, stop sign decision making is pre-planned, and as are turns. So the vehicle is not making decisions on the fly on where it needs to go. It knows what it needs to do, and then it makes decisions based on the environment to meet those goals. And so that reduces the complexity of what's required for the vehicle to do, and it should really improve the safety. And it also kind of eliminates detours. So if you have a driver that decides to make a shortcut or take a detour, you're not going to have that unknowns when it comes to driving. So that's the second piece of our safety concept. And then finally, perception. So simply put is, how does the autonomous vehicle not hit anything or avoid being hit? So perception is really the obstacle detection that we think of more when we talk about AVs, is really saying, how do we make sure that the vehicle does not hit anybody else while it's driving? So for us, it's clearly a big part of our focus. We are driving at maybe more of a commercial speed of 12 or 15 miles an hour. So the vehicle has more time to react, and we have more abilities to make the right decisions when it comes to those types of behaviors. And so for us, essentially, we've used a number of different sensors. We have sensors all over the vehicle. There's overlaps. So you're not relying on just one sensor's data. You're getting the fusion of different sensors to make those decisions. And we're also making decisions very far out. I mean, up to a couple hundred feet. We're looking at the environment saying, okay, there's a vehicle that's in front of us, but it's well ahead of us, well within our braking distance. We keep making those decisions as we keep getting closer, and as objects become closer, we make more and more decisions to be faster and faster, to the point where if someone is jumping in front of us, we're doing an emergency stop. So we're constantly scanning the environment and making decisions ahead of us to see what might be coming for the perception. So ultimately, that's the three areas where EasyMile is approaching the safety concept in different ways. And in the industry, I think is probably similarly focused on these three areas, but taking different approaches all across the board. And so I'm definitely interested to hear how we see how this is going to evolve over the next few years.
Wow. 10 minutes on the nose. Very nice, Sherrod. I love it. All right, so next up, we have Bastian from Important. Don't forget to unmute yourself.
Hello, do you hear me?
Yes, we've got you now.
Sorry, I had problems with the mic. Thank you very much. Do you see the screen?
Yes, we've got it.
Nice. Thank you very much for the opportunity to talk about the safety of people out of the vehicles. So at Important, we detect vulnerable road users, so pedestrians, bicycles, electric scooters, motorcycles, wheelchairs, anyone that is vulnerable road users. And we'll talk about the safety of these people today in the context of autonomous vehicles. So safety is an important topic. It's a top 3 fatality cause for 1 to 35-year-old in the US. And pedestrian safety has actually decreased. So there's an increase by 51% of the fatalities of pedestrians in the US over the last 10 years. And globally, there's 1.3 million people who die from a road accident every year. That's a country that disappears from the world map every 10 years. So it's a serious problem. How we approach it at Important is we develop technologies to detect smartphones and IoTs. So if you're a pedestrian and you have a smartphone, or if you're a motorcyclist or an electric scooter, you're on an electric scooter and you have a smartphone, we can detect that right now from a mobile app. And we send a prediction of your behavior to the surrounding vehicles so they can slow down and brake automatically based on the GPS coordinates of the smartphones. We've experienced a latency of 80 milliseconds of our system, and we have a precision with the new phones of about a meter, which is enough to slow down the vehicles, at least in the surroundings of pedestrians. We have also a product for information. So it goes in the HMI system. You see the surrounding vulnerable road user around your vehicle. That can be very useful for school buses, for mining trucks, construction trucks. So why do we do that? We found a study in France that analyzes pedestrian fatality causes. So it's a qualitative study. They look at the source of the cause that triggered the fatality. And they found out that there's 20 scenarios, always the same 20 scenarios that repeat over and over again for pedestrian fatalities. And these scenarios can be regrouped in 4 categories. So 35% of the time, the fatality happens because of the driver was not behaving responsibly. So this is where a lot of the sensors on the vehicle can help, making a better driver from a vehicle perspective. But 28% of the accidents also happen because there's visual blockage. So another car was blocking the view from of the pedestrian, or and that doesn't work when you put sensors on a vehicle. The sensors will not see through the car in front of them or a parked car. So that's a serious problem right now, the visual blockage. Another problem is unpredicted pedestrian behavior. What do you do if the pedestrian's cut at 90 degrees and starts to run in the street? That might be very difficult for AVs to react in time for this. And the last one we mentioned, Sharad mentioned it, the 11% of external condition can be weather, bad visibility, or darkness. That's what happened in Phoenix 2 years ago when a woman got killed by an AV. She was dressed in black at night. She was walking not at an intersection. She was jaywalking. There was no infrastructures. So that was the problem. So why do we show this and why do we study this? Well, because we can put all the technology we want on the vehicle. It doesn't solve the pedestrian problem completely. It's good. We believe in all the sensors on vehicles, but other edge cases needs to be addressed. So we're looking at this situation this way. We think that vehicle-based sensors can solve 35% of the cases, the edge cases, which is about a third. And we know that all the rest of the fatalities happen 3 times out of 4 out of intersections. So fatalities happen when people jaywalk. There's no infrastructure. The only available technology is their smartphone or their IoTs. So the vulnerable road users' sensors, possible sensors like smartphones, watches, and all these equipment have a potential serious impact in saving lives. About a half of the scenario that are not addressed by other technologies. So the takeaway today, I'll try to be really quick, but we strongly believe at important that the tech stack, the technology stack we put on the vehicle must extend out of the vehicle, and the vehicle needs to start to consider the cloud and consider infrastructure's input and smartphones input as well. And only the cloud view solves the trolley problem. So the trolley problem is when you have the opportunity to, you're going too fast, you're about to kill people, you can change direction and kill other people. Which group do you decide to kill? That's the trolley problem. It happens because the vehicle goes too fast for the detection. But if you know in advance, kilometers of advance, where are people based on their cell phone coordinates, you can slow down the vehicle way in advance and the trolley problem never happens. So this is about what we're doing as a company. We're sending data on that form to vehicles, and we tell them a risk factor that goes from 0 to 9, and 9 being dangerous and 0 being no danger at all. And so we hope that this external solution that we're proposing as a supplementary safety feature will be adopted by the industry. Thank you very much.
Nicely done. Thank you, Bastien. So let's keep moving. We've got Mario from IVEX who is up next. And Mario, take it over.
Okay, thank you, Brent. Just move this here. Okay, so thank you everybody for being here. So today we want to talk like, how do you find where is the problem, right? So my name is Mario Torres. I'm a CEO and co-founder of IVEX. Basically, what we're doing at IVEX is that we believe that traffic accidents, they belong in the past. And that's why we're helping the companies to create the safest vehicles on Earth. But how can we do this? How can we help companies to make sure that their AD and their ADAS solutions are really safe? So basically, we do this by helping companies to identify where are the edge cases and the critical situations in their autonomous driving and ADAS data sets. So basically, we know that everybody making an autonomous system, you're collecting a lot of data. But how can you find where in this data are the problems? What are the edge cases? What are near misses that you had that could have been a very bad accident, but just by luck, it was not an accident? So using our software, we believe that the way to make the system safer is really get insights on the evolution of your AD stack by using mathematically defined metrics. So we believe that we cannot just count like disengagements or very simple metrics like that. We need to have a full visibility of what's going on your AD stack. And that's what we are doing at IVEX. And today I'll show you some of those metrics that we have been working on. So basically we created a safety analytics software that then helps you to do a post-processing of these large amounts of data. This software then people can use on real road recordings, simulations, and we support different types of engineers, right? We believe that different engineers at an AD company needs to have different views on the software, because some engineers are more focused on the perception, some engineers are focused more on the full behavior of the car. And currently, it's very hard to have this full integrated view on what is going on the full AV stack. So basically, what we believe is, first, you have to really collect your data in a way that you can inspect, and then you start doing this analysis on the top of your data. So what we did at IVEX, because we said, okay, how can we get first the data to identify the interesting situations on the data? So we equipped our own Model 3 Tesla with a bunch of sensors that are normally used in AV software. For example, we have 5 cameras, RTK, GPS. Shedd, he mentioned this, they also use RTK GPS. We have a LiDAR. And then we started driving between Brussels and Paris and coming back. Even with all this COVID thing, we had a professional driver that would drive the Tesla in autopilot mode, and then it would go to Paris and come back. And while doing this, of course, we were collecting terabytes of data that we can use then to afterwards analyze. So we use this open source stack, Apollo, to see what it was inside the data. But that's not the interesting part. Can you spend 10 hours looking at data, at recordings, and then trying to find where the system was not working so well? So basically our software, it can aggregate this data from these terabytes of information and then really find to you where should you look, where your system is not working. So you can see here, and we did this on purpose. On this view, basically, we can see that this AV stack is not really working very well in terms of lane detection. You can see this clearly on this matrix when we indicate on this red color where you see that there is a lot of insufficient lane length happening when we are driving very fast. We're driving at faster than 30 meters per second, and 40% of the time, the system could not identify properly the lanes. So imagine if that would be, if we were driving the car really, you see that that would not work, because basically we would not know where the car was in the lane. But here it works very well to illustrate the point that we can identify when the system is working well or not. And then we believe that you have to get insights on what you see in terms of the internals of your AV stack and also on the behavior of the car. So let me get to the behavior. So for example, from these hours of driving, we can directly pinpoint that, for example, there is a situation here where we have a cut-in, and then we're driving at 118 kilometers per hour, and there's a car cutting us in less than 9 meters in front of us. So how could I find this in my data if I didn't have visibility on it? So basically our software pinpoints the moment that you have trouble, and then it also lets you think how you would react. Today it was interesting. We saw that, okay, RTK GPS can be very good, but we also say, when are they not working? For example, here we can see that we have this, we can also show when they're not working and when this becomes a problem, because they have an error. And if this error gets above a certain threshold, for example, this can be very bad for you. For example, if you're driving at 28 meters per second, so 62 miles per hour, and 100 kilometers per hour, and you have a GPS error bigger than 25 centimeters, this means that you can start deviating to another lane when you blink, you're already in the other lane, which would not be nice. So we believe that then one way to increase the safety of AD systems is really to make sure that you have insight on your data and that you have mathematical metrics that can follow your development so that you get confidence on your system. So who is behind IVEX? So we have been working with different companies around the world, with leading companies like Renault, Case New Holland, VDL. We have a team of PhDs, and we have workers coming from tier 1 suppliers like Magneti Marelli, Toyota Research Institute, and others. And we have companies, partners like Siemens with Mathieu that we'll talk very soon. And we're backed by great investors that believe as well in our future. So that's what we have been doing at IVEX. And I believe that, I hope that everybody agrees that we have more well-defined metrics and we give visibility for what's happening in those cars so that we can make sure that when they hit the roads, they are really safe. So thank you very much.
Thank you, Mario. Very good presentation. So Matthew, it's over to you. Tell us what's going on at Siemens.
Yeah. Try to share my screen. All right. So I guess you can see my screen.
Yes, sir. We're good to go.
Excellent. Yeah, so Mathieu Worm, I'm responsible for the domain of autonomous vehicle development within the Simulation and Test Solutions group of Siemens Digital Industries Software. And what we bring to facilitate the development of safe autonomous vehicles is a closed loop engineering environment from chip to city. So let me explain a bit what that is and why that is. So the autonomous vehicles are obviously an objective in itself to drive traffic safety, but at Siemens we take a perspective of the autonomous vehicle as being part of a solution for urban mobility issues, and that urban mobility issues is beyond safety. Obviously safety is important, but the number of vehicles that we have in cities, the massive time that's spent in vehicles standing still or trying to find parking places for vehicles is something that we need to solve. And that's why we consider an autonomous vehicle to be a component in a larger solution, of part of a solution of a larger problem. And the impact of that perspective, if we want to generate better cities, we need to develop vehicles that become computers on wheels. And the industry recognizes it, and it drives a massive transition within the traditional automotive industry, where we see big car companies partnering up with tier ones, but also with tech companies, and where, for example, Waymo is able to order 20,000 vehicles, dictating the automotive industry of the pricing of such a vehicle. We see billions of investments by traditional OEMs in tech companies. We see partnerships between companies like NVIDIA and Mercedes being formed, where actually it is NVIDIA that is mentioned first, and then partnering up with Mercedes, and where also the notice is made that it's about reinventing the whole business model. So this entire industry is under pressure, and that also has a massive impact on the vehicle development processes that these companies use. And to illustrate that, is it moves away from a traditional V cycle, and the traditional development process in the automotive industry leads to a product that is done at the end of the development cycle. And when it's done, the company loses contact with its products. And we move into a situation where you remain in contact with your vehicles, and where your vehicles actually collect data during the life cycle of that vehicle. And obviously Tesla has leads the pack there, but we will quickly see the entire industry moving into these models. Now, how we with Siemens support that new development process is by solutions to capture sensor data, to bring the capability to analyze the data, to do a diagnosis on that data, to prepare data sets for training of neural nets, to prepare critical scenario data sets, such that you can design and do design exploration on your systems, sensor configurations, sensor designs, controllers for perception, for planning, integration of sensor sets into specific vehicle contexts, and finally with validation and verification capabilities, enabling both virtual and physical testing. So as you can see on the movie, within that infinity loop picture, and we have autonomous vehicles driving around at the Setran test bed in Singapore, and we build a digital twin of that test bed to also be able to insert virtually pedestrians into the test sequences of these vehicles. To quickly look a bit into the portfolio then that is behind that, that theoretical picture. So this is data acquisition systems, onboard data acquisitions that are capable of capturing the data that Mario just described, including the position data and the vehicle canvas data, and bring that all in a synchronized format that allows you to identify critical scenarios or prepare data sets for replay for the development of perception stacks. Then we put a lot of effort in simulation of sensors. So in this movie, you see how we worked with Xenomatics, a new player in the LiDAR domain, developing a true solid-state LiDAR. We have modeled their LiDAR with an extreme level of detail, being able to synthetically generate LiDAR outputs based purely on simulation and very comparable to the data that comes out of that LiDAR in real life. Next to the LiDAR, we then also need to model the environment in great detail, such that you also have all the reflective properties of the objects around the vehicle to generate these realistic sensor outputs. And in this movie, you can see what the level of that realism is. So we see a dash cam, we see an autopilot braking at this point in time where there is no accident yet, but where the system predicts the accident that will happen in a couple of milliseconds later. And it can predict that because the radar signal can see the deceleration of the vehicle that is in front of the vehicle in front, driven by multi-bounce effects. So the beams of the radar reflect not only on the vehicle in front, but also on the guardrails and on the road itself and the bottom of the vehicle in front. Now, if we start simulating that, you can here see raw radar outputs, so that's simulated radar outputs with multi-bound reflections. And we can see that the car in front already is decelerating before the car in front of the vehicle, in front of the eagle vehicle, is doing so. So by bringing this level of realism into sensor simulation, we offer a development environment to the engineers that develop these systems to test many more different scenarios, many more variations of scenarios from behind their desk, rather than by driving around on the road looking for complex situations and the corner cases that are so important to generate safe performances. Now, obviously, you cannot manually generate millions of different scenarios. So another important focus point of the engineering framework that we deliver is automation and orchestration of massive numbers of simulations. So starting off with a database with scenarios, and it can be thousands of different scenario definitions that contain weather conditions, lighting conditions, that contain different road friction levels. We use those as an input into our virtual validation environment. We combine that with a model of the vehicle, meaning that we model the suspension systems, the tire materials, the powertrain behavior, the chassis systems. And we take those two as an input into an orchestrator that starts to generate smartly variants of the different scenarios and variants of the models that are being used from the vehicle side. So as an example, you can see here we have a pedestrian coming from behind the truck that needs to be detected by the different sensors on the vehicle. So we model the sensors, we model the weather conditions, and we can predict the time when the sensors will see that pedestrian coming from behind the truck. We can do that with different vehicle speeds, with different road friction levels, where, for example, the road friction levels with bad weather are typically lower than with good weather. So rather than that we simulate a slippery road with sunny conditions, we look for the slippery road under rainy conditions. If you run thousands, hundred thousands of runs, we can post-process all these different runs and identify the domains where this autonomous emergency braking system, in this case, has successfully prevented an accident from happening, where actually the system did not have any function, or the situations where the system failed to prevent the accident from happening. And by this, we can do data mining and an analytics on these massive results and use a falsification technology, meaning that we actively start searching for the domains of interest and that we can start optimizing the vehicle performance for relevant critical scenarios, meaning that we still run thousands of scenarios, but we don't run uninteresting, boring scenarios that will anyhow not have any impact on the conclusions of the safety assessment. So that, in short, summarizes what we bring as Siemens to the industry. So it is a lot about a closed loop process, taking in data, identifying the critical domains, and it's a lot about simulation and test and combining the virtual world with the real world to automate the process of testing autonomous vehicles against massive numbers of scenarios. And for example, coupling that into the IVEX solution for safety assessment, making it possible to do a judgment also on the performance of these vehicles. So that was my introduction. Happy also for questions in the chat to discuss further.
Very interesting. And we have a lot of questions coming up. So we will get to those as soon as we have heard what Ziv has to share with us from Fortelix. Ziv, don't forget to unmute yourself.
All right. Can you hear me now?
And we've got you now.
Okay. Thank you. So I'm the last one in between you and the coffee. Oh, there's no coffee, sorry. Okay, my name is Hil Binyamini. I'm the CEO of Autotelix. I'll talk, actually, it's a very good continuation of Mario and Matthew. We are all trying to tackle the big problem of safety of autonomous systems. So Autotelix mission is to enable the scalable and safe deployment of automated driving systems. And we do it by bringing a novel verification approach to the autonomous system industry. Okay, so just going back over the past 100 or so years, we humans decided that in order to move around, we need to build machines that will do it for us. So we invented cars and trucks and buses and forklifts and tractors and mechanical machines. But all of these machines are controlled by a human, the human driver. In the past decade or so, there is massive investment in building digital systems that will control those machines. And these are autonomous driving systems for any of these, all of these different mechanics. But we don't see yet massive deployment of those technologies. And this is because they are, in order to really massively deploy the full capability of the technology, we need full safety. We need to meet the very high bar of safety, because these systems, and everybody knows that, they are very heavy. They move fast, whether it's 10 miles or 70 miles per hour, it's pretty fast. They can cause harm, so we have to make sure that they are operating right and safe. What is the problem? The problem is that this is one of the, if not the most challenging and most complex challenge that humans so far have taken. If you open the box in an automated driving system, you'll see tens of millions of lines of code and hundreds, maybe tens to more than 100 chips, sensors. We heard a lot about sensors and processors and connectivity. And then you have machine learning. Several major subsystems are usually controlled by machine learning, or at least assisted by machine learning, like the perception and the path planning. Now, multiply this by the environment in which those automated systems need to operate. This is the most complex and unpredictable environment. Again, several mentions on pedestrians. Humans are problematic as unpredictable, not just as pedestrians and bicyclists, also as human drivers. Their behavior is hard to predict. We have other automated systems, we have weather, we have roads, topologies, and many, many other parameters. The result of this is that in order to make sure that the autonomous system is indeed safe, you actually need to test millions of scenarios. Matthew also mentioned it. And these millions of scenarios are distinct. Each one is unique and important. It's not just show me that you drove 1,000,000 miles. Each scenario is unique with different parameters, different combinations, and you need to tackle all of this. Now, when you do testing of a simple system where you need to run hundreds or maybe thousands of tests, you can do it manually using Excel. You can track what you've done. But when you move to a system where you need to test and make sure that you actually improve, that you have tested millions of different variations of the scenarios, you need an automated infrastructure to guide you through this process. And that's what we at Autotelix bring. At a very high level, the input to the system is a scenario description language. You need a way to communicate what are the scenarios. So there is a language. The language is fed into a hyper-automation engine, which crunch the scenarios and automatically generates massive numbers of scenarios. Each scenario is unique, it's valid. By the mathematical engine, it's guaranteed to be a valid scenario, and it's meaningful. And this includes going after the unknown scenarios, the thing that humans could not even think about. This then is being driven into the customer virtual environment. It can be, or physical environment. So it can be a simulated environment where all the actors are virtual, or it can be the actual physical environment. We then, every drive, whether it's a virtual or physical, we monitor and collect data. And the data includes, against those scenarios that were defined, we can collect the data to tell you what exactly have you covered, how well the system behaves, and how much of the target verification plan, how many of these 5 million scenarios that you have defined have you actually tested. We complement that by AI-based optimizers that read the results of the data analytics, this massive number of tests and variations, and uses the automation engine to drive additional tests to address areas that you haven't covered yet, or to focus on areas where there is a high risk, etc. Slightly more detail, our system is derived from MSDL. MSDL is our open scenario description language that we opened a year and a half ago. The language is used to describe the scenarios in a in a semantic that have formal semantics. So humans can understand them. Any actor, any player in whether it's a safety engineer or verification engineer or a system engineer, they can all understand exactly what they're talking about. But also the software can understand. From that, we derive the test automation. We generate all of these tests. We are integrated with many platforms, any execution platform. It can be a robot in a test track, and it can be a simulator. We are integrated with many commercial simulators and doing any integration that is needed. And then we collect information from this execution. It can be recording of a physical drive, like we've seen earlier, or it can be a virtual simulation. And we provide these metrics and dashboards. What we found is that many customers prefer that we will do the work for them in terms of defining the scenarios. So we not only provide the language that allow the customer, the OEM or tier one, to define the scenarios, we also provide libraries of ready-made scenarios that are written in this high-level description. For example, we already announced the highway and ADAS library, and we are working on an ALKS also, and we are working on more libraries of scenarios. The value that we bring, maybe the most important, is to cut down the long tail of bugs that keep coming and coming, to shorten the cycle of and getting faster to deployment of the autonomous system. Significant gains in productivity, orders of magnitude in terms of the test engineer or verification engineer productivity, increased quality, and reduced costs. For Telix, InfoTelix, we believe in openness and standards. We've been contributing to the industry. We opened our language a year and a half ago, and more than 400 companies have downloaded the spec since then. We are actively participating in the definition of open scenario 2.0, the abstract, the standard for scenario description, and actually MSDL is used in the concept project for open scenario 2.0. Both MSDL and open scenario 2.0 are a new family of scenario description languages, which are in this new scenario abstraction level called the abstract level. It's now showing up in Pegasus as a new layer above the logical and below the functional. It's the highest level, which is human readable, and is still also machine readable, so you can actually automate processes based on it. We also are participating in SOTIF, and a methodology that we are promoting, coverage-driven verification, is now adopted as part of SOTIF. So, and that's just the tip of the iceberg of the many places where we are helping, contributing to the industry. To summarize, coverage-driven verification methodology for measurable safety is a process that begins with a plan and specification, with a human readable formal specification of all of the scenarios that need to be covered, automated generation of massive number of scenarios derived from this, executed on both virtual and physical platforms. During the execution, we monitor and collect information. We then do big data analytics, and it's a closed loop. The loop is in terms of optimization, so they're automatically adding more tests, but also refining the targets, adding more to the specifications, so that this is a converging process whereby at the end you reach high quality with high confidence and metrics to prove it. Okay, thank you.
All right, great. Thank you very much. So it is 10:53. We have time for a few questions, and a number of the questions have already been answered. So thank you, gentlemen, for doing that kind of double timing things. But let's read some of the questions that are still outstanding here. So there is it looks like Sharad is actively answering one of these questions, so I'll skip that one. Here's a question from Larry. What types of sensors does EasyMile utilize? Have your products been utilized in all weather and environmental conditions?
Yep, thanks for the question. So primarily we're LiDAR based. Velodyne and SICK are the two primary companies that we've been using. So that's been the focus of that. As far as the weather question, it's a very good one. I mean, clearly that's one of the biggest challenges that's going to come up with AVs in the future. And it's a lot of combination of fusion that's going to be required. So using some cameras, some radars, and having all the different segments that give the detail together to say, the LiDAR knows there's an object there. That's very clear that we know that LiDARs can tell us when objects are there, but then determining whether that object is a car or a raindrop is really a big part of the roadmap. And it's going to all come down to how does each of the different sensors or visual devices combine together to make those decisions. Another part just very simply is just finding ways to keep raindrops off the sensors. Is another simple task that we're just kind of looking at, is just keeping the LiDARs from even detecting the rain, knowing that that's going to be one of the drawbacks.
And are you also working through how to keep the sensors clean?
Yeah, today we do a manual cleaning because we have a safety operator still as part of the system. But yeah, that's going to be part of self-cleaning. LiDARs are going to be a big part of that, because even a single piece of mud could create a different scenario for LiDArs.
Yeah.
I can chime in there, Brent. We also work with automotive companies on CFD, so computational fluid dynamics simulations, to design the car such that sensors stay clean. And you can work with aerodynamics and with how water films build up on the vehicle during the weather, and design your car such that the visibility of the sensors remains intact. For example, design of mirrors, the rear view mirrors at the outside of the vehicle, and these smaller cameras that are positioned there is a lot of attention on shaping these in such a way that the camera will always have a good view.
That's cool. And I can see the development of virtual sensors, like what Bastian's doing, will also help, in that environment.
Yeah,
absolutely.
I would also complement that what we do as well, like in our software, we can also see when the performance of the perception is not working so well. And then we can indicate that, okay, so the car should not be driving so fast, because then you can simply measure if your system is still, your sensor or camera is still seeing things properly. Then if you see that you're not detecting the lanes or detecting obstacles anymore, there's a high probability that actually your sensors are dirty. So there are many metrics you can use there as well.
Cool.
Same thing with our sensors. When we track smartphones, we have a confidence level on the whole infrastructure. So we're able to qualify the data if it's trustable or not, or at which level.
Cool. All right. Next question comes from Tom. He says, general question to all panelists. GPS seems to be central to autonomous vehicles. Curious to hear your thoughts on two things. One, how is your company approaching a GPS outage or denied environment? And two, how critical is it to have a precision service like RTK or PPP available for your product?
I can start with that one. So definitely GPS is one piece of the localization that's required. We are using a number of other LiDAR-based localizations. We're also counting the wheel turns on the maps to make sure the vehicles are in the same place. So it is one functionality of GPS, or one functionality of localization that GPS is required. So that's it. To answer your question, if there's an outage, we have some backup redundancy to support that. The NRTK is quite important, essentially to get to keep that piece on the deviation solid, so that even 6 inches from one place to another could put you into the middle of traffic. So it's important to have some reference points to that. But then again, we also have the backups on the other side of the vehicles to make sure that on the redundancy side that we're covering all angles.
Yeah. Anyone else want to chime in on that?
Okay. Yeah. Yeah. I think like Shedd, he explained, normally the localization module, you have like you fuse different sensors, and then you can use like odometry. You can even count the spinning of the wheels of the car, and you fuse these with the GPS to see like, are they nearby? For example, you see these on the corrections that you get from the GPS, and that's one way. And you can even use, like, some people, they do like a flow. You measure the flow that is coming from your cameras to estimate your speed as well. And then depending on the situation, you can use that. But I just wanted to add that in the safety critical part of the system, I didn't hear so far people using GNSS for that. So for the safety critical part, you don't rely on the localization, because basically you care about your local environment. And then basically, like, should I hit the brakes or not? And then you don't need a GNSS for that.
Yeah.
And just to complement the question quickly, GPS is essential to what we're doing so far. Actually, we're doing GNSS, so we're covering different systems, but we believe in indirect communication. So using GPS and maps are really useful to get the full potential of smart cities. Of course, we'd like the systems to work without GPS in case GPS doesn't work. So we're working right now on direct communication between phones and cars, but GPS is very a good tool right now. Even if it's not perfectly precise, it allows us to do really great things so far.
Very good. So it is 11 o'clock. I do want to thank everyone who has attended today. We're going to keep answering questions for as long as our panelists can hang out to answer them. But I realize that we're on borrowed time at this point. So I do want to thank everyone for attending, and we will get our next event posted as soon as possible. Grant is hard at work at that. So, but let's keep going here. So a question for all experts in the room: what's your vision toward the AV industry in the next 5 to 10 years? Hold on, let me write down the stock, the stock tickers for these companies. Okay, guys, go.
I think in very simple terms, I think the focus on controlled environments, airports, factories, logistic yards, even low speed density things, amusement parks, military bases, national parks, those areas, I think we'll see a lot of really driverless solutions, indoor, outdoor, without guideways in 3 years. And within 3 years, that's our target. I think in general, the industry, that type of environment at those speeds is quite likely to be very visible within our regular lives within 3 years. So at least from that perspective, we could see some changes quickly.
Anyone else want to weigh in on that?
Yeah, can you hear me?
Yeah.
I think, first of all, I think we need to give more credit to ADAS. This industry have for some reason, the biggest business going on right now that is autonomous is ADAS. This is a $35 billion business already with massive investment. I think we will be seeing incremental deployments of this technology. It's going, the complexity of the functionality is going up, and we're going to continue and see it. It's a safer, business-wise, it's a safer bet because it's an incremental as opposed to revolutionary deployment. So that's, I'm sure we'll see much more. Also, along the lines of what's called confined areas. So either more strict areas or more things that are off-road that are not within the public domain. There's less risk over there, like mines, like construction areas. There's a massive investment in these segments, as well as, places where you can drive more slowly. So, less speed equal more safety, because the damage you can do is smaller and you have more time to react. So,
and do you think do you think that ties also into passenger versus cargo?
Anywhere there's less humans involved, whether they are within or outside, then, the safety is easier, and that's an easier place to start deploying these technologies commercially. So, yes.
Yeah.
I also believe that society is really accepting more this idea of having autonomous cars and ADAS cars. And I really like that. I expect in the next 5 years, at least in developed countries, let's say, there will be a great adoption of these technologies. And I really like that, because I believe that you see statistics, there's a lot of accidents that are caused by, let's say, a lot of trucks, heavy trucks. They're involved in a large number of accidents. And I expect that those will be one of the first to benefit from this technology. And I think that's amazing, because there's a lot of families, a lot of people that just have their lives and their loved ones shattered because of this. And now we have the means to benefit from transportation without this drawback of accidents. So I think in 5 years, we'll see very different trucks driving around.
So I'll ask one question that I think just kind of unsettles me constantly. And that is, how do we successfully navigate the double standard that exists in society today, which says, if we give a 16-year-old teenager a driver's license and they go out and kill someone, well, they were only 16 years old. Like, they didn't have a lot of experience. These things happen. And we see this stuff, not beefing on 16-year-olds. I'm just saying, period. Like, humans literally kill millions of people every year, right? But yet, for an autonomous system, if you're going to take the human out of the loop, that vehicle has zero margin for error. If it ever so much as scratches someone, we're going to kill the entire autonomous effort and just take everything off the road. How do we, where is that mental paradox happening in our head that somehow those things are, how are we living with that? And it aligns directly with safety. And how do we get over that hump? I mean, is that really the truth, that we'll never have autonomous vehicles until there are literally zero margin for error?
Brent, if I may, first of all, there are two things I want to say. One, it's not the case. I mean, Tesla keeps running into making accidents that are not justified, and it's acceptable. Actually, we are accepting it. There's an accident, Tesla running in some police car or some truck every month, and that's okay. And we are accepting it. I think, to me, look, humans are accepting an accident from a human more than from a scary machine. It's just, I think it's psychology, and to me, the response to that, it needs to be, autonomous systems need to be just a bit, but in a measurable way, safer than humans, and that will be okay. And the bar is not that high because humans are not that good of drivers. So as soon as we get to that level, and in some areas we are already there, then I think humans will start to accept it because of all of the benefits.
I agree that there's a level of tolerance that is there for autonomous vehicle. Of course, it's a big drama if it happens again, but there's a tolerance and people will accept, but they will accept to a certain extent. And it depends, was the accident preventable or not with technology? And if the company didn't do its homework, or if safety technologies were missing, then it could create important damage to the industry. But if we stack the technology out of the vehicle, but include the whole smart city approach. So the question before was, what's the future of AV? For me, it's smart cities. We have to start to think out of the vehicle. We have to start to think the car talks to a pedestrian, that talks to infrastructure, that talks to the cloud, that talks to a bank, that talks to advertising, that talks to, there's a lot going on in the smart city. And in 10 years, what we'll see is smart city improvements that will drive the AV, in my belief.
V2X. All right, let's keep going with some of these other questions here. So there's a question about anomaly detection systems. How do we detect localization failures? And that kind of ties into a question from Doron that talked about, how do you make sure that the tested car module algorithm is presenting consistent behaviors? So it's kind of that whole, safety evaluation of the algorithm around anomalies and consistency.
I think in reality, it's no different than what more what the advanced cars have. I mean, you're always having anomaly detections in your cars, engine failures, and predetermined maintenance that are coming up. So it's similar for us too, is that we have parameters and ranges that need to be kept within for LiDAR detection, for localization. And if anything goes outside those parameters, there's decisions that have to be made, whether it's an error or an e-stop or that. And so we've seen that, and that's a big part of the development actually in the growth of the technology is how do you keep refining your parameters to be as tight as possible so your performance isn't affected by, how do you balance your performance and your safety by having the parameters at the optimum levels? So that's a big part of our technology actually is having those detections.
Ziv, do you have anything to add to that? No? Okay. Do panelists see a model where the freeway is autonomous and the first and last mile is either human operated or teleoperated? Oh, Ziv, looks like you're typing some in there. I mean, this model has certainly existed in the trucking space.
Yeah.
I think it's very, on a global level as well as, look, that's what, ADAS driver, you go on the highway, you put on pilot and autopilot, and then once you're getting close, so I think we'll see many models of that nature that is being described, absolutely. I think the transition from where we are today to where, I don't know, in 20 years, most cars will be autonomous most of the time. I don't know, I'm not trying to predict the future here, but during the transition, there will be many models like this where, in the the industry term is the operational design domain. While you are within the operational design domain, you let the autonomous system drive. And then when you reach the boundary when you get close. And actually, that's one of the big problems and challenges, is to identify and warn the driver when he's actually getting close, because it might be that the ODD's highway in reasonable temperatures. If the rain is, a snowstorm is coming, the driver needs to know that he needs to take over, because this system is not designed to be able to drive autonomously during snow. So that's actually the transition, and giving the proper warning at the right time is actually a technology challenge by itself.
Yeah, I can complement here as well. It's very interesting that's a very big challenge. Like when you have a system that becomes so good, people start over-relying on the system. And actually by this over-reliance, then you can have accidents. Mm-hmm. So in other industries, this is called like mode confusion. So even like in airplanes and these jets, aircrafts, sometimes you have very well-trained pilots, but they can get confused, like, is the system operating autonomously or not? In which mode am I right now? And that's a challenge, and I believe that's why we see that many OEMs, they stopped talking what it was called SAE, Society of Automotive Engineers, SAE, level 3 systems. Because it's very hard to guarantee that when you invite somebody, let's say I'm driving the car, I'm not paying attention, and suddenly the car sends a light or a beep and says, hey, Mario, take back control. Perhaps my mind is not there. And then I can think, oh, the car is still driving. Mm-hmm. And while the car is actually not driving. So that's a big challenge. And but indeed, if the ODD, if things are very well defined, that my car can only drive when I am at the highway, for example, then this avoids a lot of the problems of this mode confusion. But that's something can bring accidents.
I can see a lot of danger with these. Mm-hmm. Is it autonomous? Is it not autonomous? Sometimes it's autonomous, but I'm never 100% sure, and it keeps flipping on and off. And I just, that's what I call the mixed middle. And I think, and it extends actually even onto the road, where you have fully autonomous vehicles mixing it up with human-driven vehicles, mm-hmm. and it just doesn't work all that well, right? I mean, so it feels like the sooner, and this kind of speaks to something Bastian said, if we're going to have fully autonomous vehicles on the road mixing with human-driven vehicles, at the very least, they should be connected. The vehicles should be connected to each other to offset the limitations of the human drivers, right? So that, it doesn't allow the human driver to plow their vehicle into an autonomous vehicle. The car can take over.
Sorry, Brent, I have to run, but thank you for this opportunity.
Okay, thank you, Sherrod.
Terrific. And please feel free to email me if anyone has any questions. Great being on the panel with you guys.
Yes, thank you so much. There are a number of questions that have risen around LiDAR. Do we want to take a minute and just address, obviously Tesla has come out very strongly against LiDAR. LiDAR continues to see a lot of change and improvement and morphing into things, but we're also seeing the capabilities of LiDAR, like point cloud, definitions seeping into radar and a lot of these other things. What do you guys see in terms of the future of LiDAR and how critical they are to the safety of the vehicles?
Okay, I have a little take here, but I think this is really for technical people. There is a lot of, one take is definitely currently, if you have a LiDAR, you make the life of people creating an AV much easier, because the neural nets that you need that can benefit from the information from LiDARs, like from the point clouds that you create with a LiDAR, they're much easier to train and you get very good results currently. But so this means that basically we can evolve much faster right now. But this does not mean that we will need LiDARs in the future, which is basically actually a difference between you have an active sensor, and that has some benefits, right? Because you send some pulse of light, and then you get information back from the environment. And if you think a camera, basically there is another source of light, which is normally the sun and so on, that makes this job for you. But afterwards, the job will be the same, that you have to process what you're getting, and then you have to make a neural net that will identify what is the distance from this point, does this point belong to the same entity, and so on. So right now, I believe it helps a lot to make the system. And especially, but in the future, I don't know. But what I believe in the future, it will be a mix. Because once you have a LiDAR and you can mix this information with a camera, for example, use the LiDAR to calibrate your camera. And then when you are using both, you know that you're doing pretty well. And if one stops working, you still have, let's say, a fail-safe way to keep going. So if you see Mobileye's approach, they're doing this with a radars and cameras. But then they always want to keep one working, and you can still have a safe operation. So I hope this helps a bit the discussion, but yes, definitely it helps now in the beginning, but I'm not sure in the future it will be inherent part of the solution.
I would agree. I know on our vehicles we use both 2D and 3D LiDAR, and it has everything to do with the fact that we're operating in, we have to operate in all kinds of inclement weather. We have to go indoors and outdoors, and you've got to have that overlap just from a safety perspective. So, I agree that there are going to be new systems that come out that start to merge these capabilities, and there will continue to be improvement. But for today, I think operating without LiDAR, it all depends on your safety profile, right? And how critical that is. Although it's hard to say that Tesla shouldn't be operating at the highest safety profile. They're just not doing a fully autonomous system, that's all.
But they have a radar, right?
Brent, sorry, I have to drop.
Very good. Thank you, Ziv.
Thank
Appreciate you joining us. So I think we're kind of at the tail end here. There are Anchor has been asking about what type of anomaly detection systems do EasyMile and the other AV testing systems use. I don't know if either of you guys are familiar with that. For example, how do we detect localization failures? I see that happening with indoor localization of industrial mobile robot systems with LiDARs. I don't know, any thoughts on that? That might be one that I have to punt to Sharad and have him answer later. What do you guys think?
So here, there are many ways actually. Like in our metrics, for example, in our software, we have different techniques that we use to detect localization failures. But you can think a very simple algorithm is how much is a jump that you have and what are the assumptions you have about your system. I'll be very more concrete here. If you have a car, you know that a car cannot move laterally unless there is a huge truck hitting the car. But having this assumption, you know that if suddenly in your localization you have a jump laterally on the car, for example, and you know the reference where the car drives forwards, you know that something is wrong. Mm-hmm. That's one thing that a very simple heuristic, but of course you can see that you can start building upon this kind of techniques to get a very good view on, can I still trust my localization?
And does IVEX's system flag that as there was an anomaly that happened here?
Yeah, we flag the situations, what we call events, and then that's actually what I showed in the map. Mm-hmm. Then basically at that moment we said, hey, the GPS is not working as we expected, because the intervals on this localization, they were much bigger than what we believed it should be.
Got it.
It was like more than 25 centimeters, while we expect to be less than 5. So yes, we flagged that.
Very good. Well, I think we've answered the majority of the questions. Did you guys have any last comments to make before we wrap it up? The floor is yours, given there's only 2 of you left.
Well, thank you everyone for being here. It's been awesome time. The only last note we'd like to bring is really the concept of bringing what we talked about, the tech stack. So to use many technologies doing the same thing, to have a robust approach. This has to extend out of the vehicle for safety reasons, for other reasons as well. But if we consider safety, we need all the technologies possible. Like it's a real challenge, and it's not one technology will solve the problem. It's a combination of many technologies together.
Yeah. Very good.
Yeah.
Well, Mario, I know it's late for you.
Yeah, my wife will fight me this evening. So, so yeah, well, first of all, thanks a lot, Brent, for organizing this. It's very nice seeing you again. And in terms of safety, what I like to see is 2 years ago, when we were in Silicon Valley talking about, hey, how do you guarantee the safety of your system? Everybody was like, that's ultimate, important, and super relevant, but we're busy training our neural net with this new data that we're capturing. And right now, since last year, we see that now when we talk to OEMs, to tier ones, everybody's more like, hey, yes, we have to solve this. We know that there's no way to deploy the systems. And I'm very happy to see that the whole industry is really takes this very seriously, and that there is a whole bunch of smart people working very hard to make sure the systems are ultimately safe and that there will be no harm. So yes, I like that, because if we follow the same patterns as in the airline industry, the airplanes industry, the cars will be, like you said, much better than human drivers. I don't believe we're already there, but we're walking to that direction, which is very good.
I think we've got a good future ahead of us. Well,
Yes.
Thank you very much, gentlemen. Thank you for everyone who has participated. We are going to wrap up the February event for Self-Driving Cars 101. And I want to thank you all for your attendance, and especially for the fantastic panelists. Appreciate it, guys. Have a wonderful weekend.
Thank you. Bye-bye. Have a great day.
Thank you.